Hey everybody, welcome to Simple SIMD using ISPC, the Intel SPMD program compiler. I'm Pete Brubaker, joined here with my colleague John Kennedy. So Intel Eagle is going to make me read this all out to you guys, so we'll just sit here for a few minutes. You guys can hear me read this legal disclaimer. I'm just kidding, they just want me to show it for a minute, but so yeah, brief introduction. Who are we? I'm a veteran game developer. I've worked in game development for over 10 years. I started as a technical artist and then spent most of my career as a graphics and systems engineer. I'm credited on more than 10 titles from companies like LucasArts, EA, Rockstar. And in the last 10 years, I've joined IHVs like Qualcomm and Intel to develop tools and technologies to help you succeed on mobile and desktop platforms.
Yep, and I'm John Kennedy. I spent my career predominantly in graphics. So in the 90s, I was doing VR, first time, or second time around, I guess. Worked on games, worked on DevRel, a whole bunch of things. I currently spend my time at Intel in developer relations. Been playing around for quite a while now with ISPC. One of the projects I've been looking at is an ISPC backend to SPMD cross to help people move all of their compute from the GPU to the CPU.
So why are we here? Well, exploiting parallelism is pretty essential for obtaining performance on modern hardware. We know that. We're all dealing with multi-core hardware these days. And so there's two types of parallelism. There's task parallelism and SIMD parallelism. And I think most of us are familiar with task parallelism, where that's multi-threading on multi-core machines. And not too many of us actually use SIMD parallelism. So we're here to talk about that. So can I get a show of hands? How many people have written vector intrinsics before in the room? Wow, more than I expected. So like, how many of you are like, say, if I sat you down and said, hey, optimize this particle system, how many of you are like 50% or more confident that you could do that in a reasonable amount of time? Okay, cool. And then who are the vector wizard ninjas in the room that know the vector ISAs like the back of their hand? How many people in here would say they're an expert? A couple. All right. So that's about what I figured. More of you have written vector intrinsics than I had expected. So yeah, it takes a long time to learn this stuff. That's the point. And there's really no time to do anything cool with it if you spend a lot of time trying to learn it. So how can we make it easier to get all the flops without being like the one or two vector intrinsics ninjas in the room? Well, I think ISPC is that answer. So what does ISPC stand for? ISPC stands for the Intel SPMD program compiler. It's a compiler in a language for generating vector code, writing vector SIMD code. It's open source. It's based on the LLVM backend, and it's a compiler for many SIMD architectures. It generates high-performance vector code for SSE, AVX, AVX2, and AVX512, as well as Neon. And I will say that Neon support's kind of experimental and supported by the open source community. The language looks a lot like C, so it's simple to use and simple to integrate with existing code bases. What is ISPC not? ISPC is not an auto-vectorizing compiler. It doesn't analyze your loops and automatically promote things to vectors and do it like ICC or Clang or GCC or MSVC. It's more of a WYSIWYG vectorizing compiler. You, the programmer, tell ISPC what's vector and what's scalar, and vector types are explicit and not discovered. So it looks, like I said, it looks a lot like C, so it's easy to read and understand. And here's an example of a simple kernel in ISPC. It's called RGB2 gray. You'll see this throughout the rest of this presentation. Essentially, it's taking an RG and B value, multiplying by some scalars and summing it into a gray value. So this code looks very sequential, except for the new for each thing. We'll get into that. It easily mixes scalar and vector computation, and it uses explicit vectorization using two new keywords, uniform and varying. We don't see them here because for each does that kind of for you, but we'll get into that a little bit more. Again, ISPC is not an auto-vectorizing compiler. It's basically like writing shaders for your CPU. So here's the key concept that I want you to take away from this talk. There's these two keywords are what essentially makes this language work. Uniform is scalar data and varying is vector data. So the uniform results in like a scalar register like EAX, EBX, ECX, etc. And all SIMD lanes or all varyings would share the same value. And varying is vector data. It results in the assembler. It results in a vector register like XMM, YMM, ZMM. Varying is the default. So if you just say float data equals 0, you'll get a varying. You have to explicitly state that it's a uniform. With a varying, each SIMD lane gets its own value. And the width is dependent on the target that you tell the compiler to compile to. So for SSE, you would have 4 elements in your varyings. For AVX2, you'd have 8, and for AVX512, you'd have 16. So let's take a look at some example assembly output here for a second. Here we've got our RGB to gray. And with a for each loop, we're going to iterate through all of those arrays and perform that computation and store it in the gray array. And this is what's generated from the compiler. Essentially, there's some more stuff going on here for the for each, but the inner loop of the for each generates 3 loads, 3 multiplies, 2 adds, and a store. And that's pretty good. So why is this good? Well, you, the programmer, no longer need to know the vector ISA to write good vector code. I did some research, and there are over 10 vector ISAs just on Intel alone with over 10,000 instructions. And that's a lot for a human to remember how to use. It makes it more accessible to people that aren't familiar with SIMD intrinsics. So you learn this language instead of sitting down and reading a vector ISA. You'll have more programmers on your team able to fully utilize the CPU in various areas of game development. It's easier to read and maintain. It just looks like scalar code. Supporting a new ISA is as easy as changing a command line option and recompiling. And typically converting scalar code over to ISPC, you can expect like a 3x or more speed up with 4 wide SSE and like 5 to 6 using 8 wide AVX2. Possible to get more. ISPC has a couple of double pumping targets, but we'll get into that in a little bit. But these are typical numbers. So where can we use this stuff? Well, lots of places. You saw yesterday in the Intel or in the EPIC Chaos demo, we used ISPC to optimize the Chaos physics engine. Particle systems, skinning. I think it has a huge benefit. Could have a huge benefit to asset pipeline, where you can control the hardware that you're running on, and use it on your build farms and in your tools code. Compression, decompression, intersection testing was part of what happened with the EPIC demo yesterday, and image convolution, and like really the only limits your imagination. And for an example, Intel has the Intel Embry ray tracing kernels, and we ship those and Osprey, and those are all pretty much written in ISPC. So let's take a look at a couple demos here. When I started learning ISPC, I wanted to pick a bit of software that was fun, that I didn't know anything about, that I just wanted to optimize. And I picked Yoast Stom's Stable Fluids source code, and I optimized it by copying the source file to an ISPC file and then adding uniform and varying keywords in the right spot. And so this is running CPU scalar about 50 milliseconds per frame. And I'll switch it over to ISPC. This is on AVX2, and we're running about 5 milliseconds a frame. So we're about 10x faster. And you're saying, okay, well, wait, why are we 10x faster? AVX2 is only 8 wide, so you should hit a theoretical limit of 8 times faster. But like I said, ISPC has a couple of double pumping targets, and this was compiled with AVX2X2, and so it's simulating 16 wide. So that's why we end up with the 10x performance improvement. And again, like I didn't do anything to the underlying source code other than add uniforms and varyings. I learned the whole language and did this in a day. And then John will show something else.
So this very much along a similar theme. So this is actually on GitHub. You can go to the Intel GitHub and download it to have a look. So this is based on the Microsoft N-Bodies particle system for DX12. And the whole idea here is exploring the idea of, can we take GPU compute code and explore putting it on the CPU? The idea here is very much, the GPU is generally doing a lot of work. If you know that the CPU is underutilized, then we can move things over. And so with this, we've got a couple of kernels. So this is the scalar C++ code. So pretty much like Pete's, just to show you where we are. So we get in 8 frames per second, 120 milliseconds. So not great at this point. Whereas this is the ISPC version. I'm using 8 threads. It's using AVX2. And yeah, we're going around, give or take, 8 times faster. So this is a very easy win, just taking the code pretty much straight over, as Pete said. And as you find out in the talk, there's a few modifications you have to make to the language, put a few of these new keywords in, but that's pretty much it. You're good to go. And again, porting this code from HLSL took, in the region of half a day to a day, a little bit of glue code. So yeah, pretty simple.
All right, so let's go into some depth with the language a bit. So to quickly recap, effective use of uniform and varying is the most important concept to grok from this talk. You, the programmer, specifically state what's vector and what's scalar. The vector types have a fixed vector width chosen by the compiler at compile time. So when you specify SSE4, you'll get 4 wide, AVX2 is 8, and AVX512, 16 wide. And again, it's typically how many 32-bit values fit in your target CPU's vector registers. And we're going to cover this one more time just because it's that important. I want to make sure that you grok it. Because you can literally write SIMD code, ISPC code, without using any of these other fancy constructs that we're going to go over if you just understand how these two keywords work. All right, so mixing uniform and varying typically works pretty well. You can assign a uniform to a varying, but you can't assign a varying to a uniform. Uniforms get automatically promoted to varying. So here we've got a uniform float 0, and we're going to assign that to a varying float zeros. And what we've got on the top and the bottom, the top uniform is essentially broadcast into that varying. And then this is an example of why assigning a varying to a uniform won't work. We can't take all of that data and collapse it down into one register, one 32-bit register. So these are, I wanted to show some C code on the left and equivalent ISPC code on the right. These are both scalar. I just wanted to show that if you wanted to port something on the left before you even get into using varying, you can just copy your code, if it's C, add uniforms in the right places, and you'll get a scalar ISPC output. So scalars are nice and all, but where's the vectors? That's where varying comes in. No varying means you don't get any vector code. So let's take a look at what our kernel on the top here is doing. We're just taking a RG and B value and multiplying it by a few scalars and summing it and adding it into one gray. So that's what it looks like as a uniform. And then here's the bottom one. We have varying inputs to the function, and we're essentially doing 4, 8, or 16 wide the above function. So ISPC has two built-in variables to describe the vector width for you. It's got program count and program index. Program count has a type uniform int. It returns the vector width used in the compilation unit. So if you compile with SSE, program count will be 4. If you compile with ABX2, it'll be 16. And in this case, again, the number of 32-bit values that are packed into a vector register. And program index has a type of varying int, and it is initialized to 0 to program count minus 1. So for SSE, that'll be 0, 1, 2, 3. It's useful for indexing into arrays from a uniform base. So here, like if you're doing a loop and you're 4 wide, you'd be incrementing your I by 4 every loop count. And in order to index into an array, you would take your I plus program index and then dereference your array. So arrays, they work pretty much as expected. Arrays of uniforms are just like C++ arrays, so it's uniform layout in memory. So if we take a look at what some of these array dereferences are doing here, so we're taking uniform input 1 here, we're taking the first element and doing a scalar load into a uniform. And then here, we're taking input 1 and dereferencing it by program index, again, like 0, 1, 2, 3. And so we'll get the 0th, 1, 2, and 3rd element of the array. And that'll result in a vector load. And this is kind of weird code, but we're taking the result of input 1 bar, and we're using that to then index into that array again. And the compiler will generate a gather here for this because it doesn't know that if those elements of memory are linearly arranged in memory. And then lastly, we're taking the first element of input 2 and assigning it into a varying, and that gets auto-promoted to varying from uniform, and that'll be a broadcast into that vector register. So pointers are a bit more complicated. The variability is specified like const in C and C++. We found it's best to specify the variability so that it's clear to the reader and anyone else that might come along to look at the code later. The variability has two parts, the pointer itself and what it points to. So you have to specify if it's a single pointer to multiple things or multiple pointers to multiple things. It gets a little bit complicated. So let's take a look at it real quick. Here we've got a uniform pointer to a uniform memory location. And this is typical C and C++ pointers. Here we have a varying pointer to a uniform float. So we have a pointer per lane that points to some random memory location. And then we have a uniform pointer to varying floats. We have a single pointer to 4, 8, or 16 floats. And so structures. Technically, ISPC has 3 different types of variability, uniform, varying, and unbound. Unbound only happens with structs. And unless explicitly labeled, structs have unbound variability. The variability of unbound members is determined with instantiations of that struct, and the variability is recursive. So like if you have a struct within a struct and you declare it a varying, then that variability applies throughout the hierarchy of the structures. So what does that look like? All right, so we've got color here, R, G, and B. Float members, and then we have 2 different instantiations of this struct. We have uniform color pixel, and we see if we uniform color pixel, we have R, G, and B, and then this is how, like if we had an array of these pixels, that's how that memory would be laid out. And then we have varying color fancier pixel, and what this does is it expands the members of that structure out to the width of your compilation unit. And this is called hybrid, or a lot of people call it different things, but array of structures of arrays. So where if you dereference R in fancier pixel, you'll get a vector load. But if you dereference R with pixel, you'll have uncoalesced memory accesses. So here is an example of that. So let's say we want to dereference program index upixels R. So since our memory is not our elements are not aligned in memory linearly, we have a gather. So we have to uncoalesce memory access to get that. And then in varying V pixels, we repeat chunks of red, green, and blue of the compilation target width, and we get vector loads, which are much faster. And to give you an idea of what this looks like in your CPP code, your CPP side struct will have R, G, and B, but they'll be small arrays of where VLEN is defined as the width of the compilation target, like SSE and AVX2, so 4 or 8. Here's another example of how the recursive variability works. Again, we've got our color struct, but in struct alpha, we add a float. And if we declare that as a uniform, we get this memory representation. And if we declare that as instantiate it as a varying, we get this memory layout. So for control flow, ISPC has pretty much all the control flow constructs that you'd find in C and C++, but it also adds several new ones for convenience and performance that we'll get into. For each and for each active and for each tiled and for each unique are pretty useful. And CIF, CWhile, and CDO, the CIF, CWhile, and CDO are for when you're operating on a varying. So if you're essentially telling the compiler a hint that you believe all of them will be coherent. So if you do an if test on a varying, you'll be doing essentially a masked if, and you're telling the compiler that I believe that in most cases of you doing this if, they're all going to result in the same output. So one important thing to understand here is how you would use program index and program count for parallel iteration. This is kind of like what for each does for you, so I wanted to cover it in the talk. So in a for loop, program index and program count can be used to iterate over chunks. The loop counter is incremented by the program count, and the data is indexed using I plus program index. And so you'll see that in the loop, we promote that I plus program index gets promoted into a varying, and then we use that varying int to dereference our arrays. It's pretty much equivalent to using for each with one caveat. The n must be a multiple of program count. So there's no masking going on here for remainder iterations of your loop. You have to assert on your input data that n is a multiple of program count. So the special iteration constructs for each is really cool. You can iterate over the range 0 to n in chunks of program count elements. The varying variables, like you can use I, j, and k. I think it supports up to 4 or 6. And it operates like you would have nested for loops. In this case, though, the remainder iterations are going to be properly masked. For each active is also pretty cool. You can serially iterate over a varying value. And then for each unique is the same sort of thing, except you're serially iterating over the unique values in a varying. So if you had like a 4-wide vector and you had 0, 0, 1, 2, your loop count would only, with for each active or for each unique, you would get 0, 1, and 2, and you'd only have 3 loops. So ISPC provides a pretty rich standard library of operations. I mean, I'm not going to read them all out to you here, but like math and bit ops and all that stuff. The random number generator is not the fastest. You can probably find a better one to use online. We have multiple implementations for math, the standard fast, short vector math library, which I don't really recommend that you use. And then the system math library, it's high precision, but scalar only. And all of these are selected by the command line switch. So ISPC is pretty awesome for you at generating the vector code, but it can't rearrange your data, and it can't speed up memory accesses. So data layout is pretty important. Your data needs to be in cache, and it needs to be in the right layout. Pardon me. Gather and scatter instructions are painful, can be painful, especially if they're in inner loops. So prefer structure of arrays or array of structure of arrays memory layouts, as these will all generate vector load stores. And if you haven't seen Mike Acton's data-oriented design talk from CPPCon 2014, he lays out pretty compelling reasons for if you're writing high-performance code, your data layout is pretty important. So I highly recommend you check out his talk. So let's look at this in pictures instead of words. So in order to obtain peak performance, your data may need to be transposed. And typically, the cost of transposing this data is less than the cost of using gather and scatter instructions. But definitely prefer structure of arrays or hybrid structure of arrays, array of structure of arrays. It does, however, ISPC's standard library does, however, provide some array of structures to structure of arrays helpers. There's AOS to SOA 3 and 4. It loads 3 or 4 times the SIMD width using vector loads and then shuffles the data into the correct layout. And then the SOA to AOS functions, convert it back so you can store it. It does require the data to be interleaved, and it doesn't really support complex structures. So let's take a look at what this does. So first of all, it's going to do a vector load of 3, in this case 3x the SIMD width. And then it's going to shuffle the data into a proper varying so you can do your work. And then this function at SOA to AOS 3 is going to shuffle that data back, and then it's going to do 3 vector stores. And this is pretty quick. I mean, it's not as quick as just doing a vector load, but it's not. If you have data that's laid out like this, and RGNB is pretty common in games, then this is almost as fast as redoing your data. ISPC has some other language features that we aren't really going to be covering covering today, but I wanted to give you a short list of some other stuff that's available. It supports references a lot like C++. It does support binary operator overloading on structures, and it has a built-in multi-threading system that enables fork join multi-threading, though in your case as game developers, probably better to just use your existing task system. All right, so I'm going to hand it over to John here, who's going to take us home with how do you actually use this stuff.
All right, well, thanks, Pete. So Pete's done a really good intro there, or perhaps why you should start using it, some of the language features. I want to now cover how to actually use the compiler, I guess, rather than the language side of things. I mean, with the language, the main things to think about are we've gone over what's uniform, what's scalar, and what's varying. The varying, generally, when you're writing your code, is an abstract notation. So you don't need to worry about if it's 4 wide, 8 wide, or whatever. Just think of it as abstract. And then as we get into it, you get your concrete instantiation. So first of all, anyway, we have the compiler. So we can download this. It's open source. We've got links towards the back. You can download the binaries for Linux, Mac, and Windows. And it will compile. It will produce executable code for you, object files for Linux, Mac, Windows. I believe there's support in there for PlayStation, Xbox. But one of the main elements, because it's open source, if there's a platform that we currently don't support, just download it, compile it to your tool chain, and you're off. In terms of the targets, as Pete was saying, whether you're targeting SSE 2, 4, AVX 2, AVX 512, all of these you specify at compile time when you compile your kernels. So when you write your code, if you think of it purely as an abstract vector, you don't worry too much about the width. If you try to keep the specific width out of your algorithms, then it's super easy just to get it working in all these different instruction sets. And I think that's really one of the key elements that Pete alluded to earlier on, that if you're one of these intrinsics ninjas, you know that it's taken you perhaps months to work in your SSE4 code base. And you're very proud. You've tuned it. It's really, really good for the performance side. But then you produce it as for AVX2, and it's just going to take months of hard work. But with ISPC, you simply add that new target on. You've already got your kernel written. you just recompile, and that's it. It's retargeted, as simple as that. So the target's command line interface option, it produces a few files for you. So by default, you'll get a .o file, and this contains obviously the meat of what's going on here. That's the actual code. There's also a header file which gets output. And so one of the things that we didn't mention is ISPC is a very, very lightweight framework. And some people, it might be used to perhaps using OpenCL to try and target the CPU and to try and get the most out of it. OpenCL is a good language, it's a good API, but it's very heavyweight. You've got to pull in a pretty fat runtime, pull in the DLLs, separate compilation phases. ISPC is the exact opposite, really, really lightweight. In terms of the API is just what you define in your kernels. So you write a kernel, and that becomes the API. You call it from C, and you're off. And it's also good to note that you can output assembler if you want to have a look at it. You can also have a look at some of the LLVM IR. And then, the resultant object files, we just link into your project. And really, with this slide, I guess we just wanted to show you how simple it really is to get going with ISPC. You know, we've got a whole bunch of online material that you can have a look at, but go to the website, download the binary, install it wherever you need on your path, create your ISPC kernel. Typically, it'll be a .ispc file. And number 4 here shows what you do. You call the ISPC executable. You pass in a target of perhaps AVX2. You have your kernel at the end, and that's it. It's simple. It will compile it, and assuming you've got clean compilation, you then will get your .o file, your header file. You add your .o file to your linker. Your .h you obviously add into your C, C++ code. You do the integration that's needed to call into your actual kernel, compile it, and you're off. It's really simple. And I mentioned the API, and it's kind of how do we create the API? You know, if you're a 3D programmer, perhaps you're used to calling dispatch with a ND range on there. Well, this is very, very different. So you define it as the programmer. So in the examples we had earlier with the RGB to gray API calls, all we need to do is prefix that function with export, and that's it. That suddenly becomes your API. So if you want in your kernel, you can have 1 API entry point, you can have a dozen. It's up to you. Just whichever function you prefix with export, that will auto-generate the header file for you, that you then just call from your C, C++ code. And so for that, to make sure that you can call into your ISPC kernels correctly, the assumption is that all of the parameters that you pass in are scalar, obviously so they're uniform, because your application code is not aware of the notion of varyings. There is one exception, and this is uniform pointers to varying data. So this is allowed. And so one of the main reasons this is allowed is often there'll be perhaps a design pattern where you've got your code you want to work on. The first thing you do, as Pete was suggesting, perhaps it's in an array of structures, you want to convert it, you want to transpose it. So you perhaps have your kernel, which does that transposition for you. You pull the data back into your C code, you then call another kernel, which does all the work, and then at the end, you can transpose it back again. And so that's kind of why we have this. Obviously, if you're going to try and dereference this varyings from your C code, be careful, make sure you know what the vector width is that you're working on. ISPC generates the header, as we said, so all of your exported functions will get put in there as your API. But also, if you have any structures that you define that you need to use. So for Pete's example, you had your pixel, or even your fancier pixel. They will come through in this header file, so you can simply use them within your C code, call into it, and you're off. And it's worth noting that when you call into your ISPC kernels, there is an assumption for performance reasons from ISPC that there is no memory aliasing. And so it won't stop you, it won't warn you if you do alias your pointers, but yeah, bad things may happen. In terms of the generated code, so ISPC aggressively optimizes for speed. So you might find you write lots of nice code, you've got lots of nice little inline functions throughout, but when you actually come to look at the assembly, they're all gone because it's all very aggressively inlined. But that's good, that's what we want. We want the performance. However, when you actually look at the assembly, you might find there's a lot more code in there than you anticipated. And so this is one of the reasons. We've got all this inlining going on. You might find multiple versions of functions. Perhaps there's a function where there's a masked version and unmasked. And by that, we mean if you know that all of your SIMD lanes are active, then it won't mask out SIMD lanes, and it will just run this code on all SIMD lanes. Or perhaps you're at the end of one of the for each loops that Pete was talking about. Perhaps you've only got 4 active lanes out of 8. Therefore, you need the function to be aware of that mask. So there's a whole bunch of stuff goes on. When you start looking at the assembler, you will see this, but don't be alarmed. It's purely there for the performance reasons. So a key part of ISPC, as we were kind of saying earlier, is the fact that you can target multiple instruction sets. And this really is as simple as putting them together on the compile line. And so you can chain these together. So you could have AVX2 and AVX1 and SSE4, or whatever you choose. And I think this is really important, certainly for the gaming community. We know that a lot of people still use SSE4. AVX2, I think, was invented by Intel in the Haswell period, which is 2013. So it's been around a really long time. So AVX2 should certainly be your base across most of the PC systems. But if you want to support those legacy systems, that's fine. We just compile for SSE2, compile for SSE4, AVX2, whatever. It will generate multiple object files for you. You simply link those in, and you still only have your one header file. And this is one of the crucial bits. You have the one header file, and I said earlier that ISPC is a very lightweight runtime. It is, but it does some smarts for you. And at this point, it has what we call the dynamic dispatch. So it will work out what instruction set it is running on. So it will know if the best instruction set for the current PC is perhaps SSE4 or AVX2. And assuming you have those compiled in, it will then set up a dispatch table for you. So you will then go straight into the relevant function. And there's a slight overhead for this, obviously, 17, 18 cycles. But generally, you're doing a whole bunch of work, so that's fine. And if you're just targeting one instruction set, you don't get this overhead. You just go straight into that function. Pete mentioned earlier as well, there's some of these double pump-in targets. So SSE4 times 2, AVX times 2, and so on. These are really useful, definitely worth exploring. As Pete said, he found some extra performance by doing that. It helps hide some of the memory latency and things. But beware, it's not always an optimization. So if you do this, you're going to use more registers. As a result, you might get spill and fills, spilling out to memory. So you might find there isn't actually performance to be had there. But definitely worth experimenting. Debugging. This is always one of the topics that comes up. It's kind of great. I've written all this performance code, but how do I go from debug it? Fortunately, it's simple. As of a couple of versions ago in ISPC, you simply add -G to the command line, and at that point, you'll get some of your debug symbols, which nicely integrates with Visual Studio, with GDB. You pick your favorite debugger. The thing to be aware of, though, with the -G is you will still get a lot of the performance optimizations that ISPC generally does. So I kind of liken it to trying to debug release code if you're looking at your standard application. So you'll find at times that with all the inlining, perhaps that's a bit of an issue. Some of the variables perhaps have been optimized out. But you can step through your ISPC kernels. It's integrated to that extent. You can also look at the assembler. So you can go through the assembler, look at the registers, and see what's going on. So it's very, very useful at times. But if all else fails, we've always got printf. Everyone loves a printf. So we don't actually have the fully fledged printf. It's kind of a cut down version of print, but it works really well. You can print your uniform data, you can print your variant data. So sprinkle this throughout your code, and it's a really nice way to see what's going on. For the hardcore amongst us, if you want to actually look at the assembly. Then again, this is just a command line option to dump out the ASM. You're going to have a look at the LLVMIR. And if you're that way inclined, you can work out quite a lot of information from this. And definitely, even if you're not that way inclined, try it. Have a look at it. It might not be as scary as you think. So to make life a little bit easier for us, we have the Compiler Explorer. So I don't know how many of you are familiar with this. So Matt Godbolt, a few years ago, invented this really impressive tech online. So you can go onto the website, godbolt.org at the bottom, and it allows you to basically write C code, C++ code in your browser, and then you can choose what compiler you want to compile it with. It will compile it for you up there in the cloud, and you can have a look at the output assembler. So really, really nice to try different combinations of things, different compilers, really good for trying to dig into optimizations. And the good news for us and for you guys is Matt added ISPC to that some time ago. And so for me, whenever I'm programming with ISPC, this is one of the pages that I always, always have open. So go to Godbolt, you can experiment, you can put your kernels in there, you can play with different targets, you can see what the assembler looks like, you can see if you've got gathers or broadcasts, you can see what's going on. And it's a really nice way just to tweak things and try and get the most out of it. And the example here, so this is essentially what you see when you go onto the website. So on the left, you just put your kernel in there. On the right, you'll see the assembly. And at this point, you also get some nice color code in. So the main inner loop there, which is doing the gray RGB, I guess, to grayscale function, we see is being nicely compiled here to AVX2 with a few mass moves, broadcasts, few FMAs. And so it's generating the code we were expecting, so it's nice and efficient. So something else that we have to help you guys with ISPC is Pete recently wrote the Visual Studio Code plugin, and this is now live online. So this is a language server for those of you using Visual Studio Code. It does all your syntax highlighting as you'd expect, auto-completion, a whole bunch of stuff. It'll go through, do some validation for you to poke at some of the errors and warnings that you might get. Really, really useful. You can go on there now. I think Pete released it literally about an hour ago. So go check it out, search for ISPC, and get coding. Finally, I want to give a quick shout out, I guess, to Matt Farr. So without Matt, ISPC wouldn't exist. So Matt started working on this many years ago, 7, 8 years ago, whilst he was at Intel. It started off being a little research project, but now it's turned into the product that we're all using and we're all talking about. And I'm sure if you haven't seen the epic Chaos Engine demo yet, go and check it out. That's all done with ISPC, getting really good performance. Matt posted an interesting blog all about the development of ISPC. Definitely a very colorful read. It's worth having a look at. Also want to thank James and Dimitri, who are, I guess they're the most recent shepherds within Intel who have been helping drive ISPC forwards. And most of this talk is based on their content from previous talks. And then the very last slide, we want to just collate a whole bunch of resources for you. So go and check this stuff out. There's the ISPC website. If you go on there, you'll find all the user guides, performance guides. And again, when I'm writing my ISPC code, I generally have Godbolt open on one browser window. I have the user guide and performance guide in another one. These are definitely your go-to websites. We've got a whole bunch of articles as well on the Intel Software Developer Zone. Check them out. So you'll certainly find the particle system that we had on there earlier on there. It's on GitHub. You can go download it, have a look. There's a nice tutorial as well, which talks you through how I converted from HLSL to ISPC. We try and go through in all the different steps. So that's a really good starting place. If you download ISPC itself, it comes with a whole bunch of sample code. So again, have a look, just compile it, go through it. Shout out to the vTune team. So ISPC works well in vTune. If you want to try and find your performance hotspots, run it through vTune. And if you're not aware, vTune is now free, so go download it. There's no excuses not to start profiling your code. And you'll see, just as we did with the debugger, you will find that your ISPC kernel is now profiled with the hotspots. You can dig into them, so you can go to the assembler as well, depending on what level of analysis you want there. But really, really useful. There's also the original white paper, if you want to go and have a look, that Matt Farr wrote with William Mark. And we have a support kind of user group on the Google Groups, which is the ISPC users, you can see here. And if all else fails, give a shout out to Pete, myself, Dimitri, you're all on Twitter. Go out, go and explore ISPC and see what goodness you can come up with. And that's it. Thank you very much. So if you have any questions, please come up and shout out. It's very hard to see, so do wave and flag.
Oh, yeah, there's also a mic in the middle of the room. No questions, really?
In that case, I guess everyone's waiting for the raffle.